So this last unit that we're covering here is all about kinematics. All right, kinematics. Now, this word kinematics, there's another term that means basically the same thing, and that's rectilinear motion. Okay? Rectilinear motion. And basically, I'll just come over to the side here to explain this. Basically, what we're talking about is motion along a linear path, okay? So we're modeling something with respect to time, but it's only linear, okay? So we might be looking at something's movement up and down, okay? Maybe something's going up and down. For example, if we were going to model your height off the ground if you're riding a Ferris wheel, okay? Obviously, your physical motion is going to be in a circle, but if all I'm looking at is your height, then you're going to be moving up to here, and then back down to here, and then up to here, and back down to here. Okay, and as you can see, that can be kind of difficult to model. So what we do is we then would model it using a graph where the independent variable is your time and the dependent variable would be your height at a given time. Okay? Now, we're going to examine an illustration here related to this, but the main thing that we're talking about in this case is what's called our displacement. Okay, our displacement. And there's a couple of pairs of terms that we're going to be dealing with here. One is displacement versus distance. Displacement versus distance. And the other is velocity versus speed. Okay? And we're going to look at some applications and things, and really the vast majority of what we're doing in this unit is going to be dealing with these and then also acceleration. Okay? So, let's look at a couple of things first, and then we'll get into some of the terminology and notation at the end. So, let's look at our situation we've got here. Michael lives on the opposite side of a hill from his friend, okay? So he leaves his house, he rides up a hill and down the other side to his friend's house. The dots on the graph show his position at various times, okay? Now this is what's known as a motion diagram. Okay, so from Michael's place to his friend's house, notice here it's taking him a total of 19 minutes to get to his friend's house. All right, but you'll notice also that the amount of distance that he's covering is not the same for these different time intervals. For example, notice here from 0 to 5 minutes, in the first 5 minutes he covers that much distance, but then from minute 5 to minute 10 he only covers that much distance. Now why do you think that might be happening? Yeah, he's going uphill, all right? So he's able to cover this much distance in the first 5 minutes, but evidently the hill must be getting steeper or something like that in here. So he's slowing down, okay? He doesn't cover as much. And if you've ever ridden a bike up a hill, you know what I'm talking about, all right? It's harder to ride. Even if you have different gears you can put it into, you're going to end up slowing down, okay? But then you'll notice here, again between 10 and 15 minutes, we don't cover as much ground. But notice in this 2-minute time span, from 15 minutes to 17 minutes, he covers this much distance. So what must have happened here?
Downhill.
Yeah, he reached the peak there somewhere around the 15-minute mark. And now he's cruising downhill and going a whole lot faster. Notice he covered about as much ground in those 2 minutes as he did in the first 15 minutes. Okay? And then again, the last 2 minutes, he's still going fast. Okay? Now, we can model this a number of different ways using this motion diagram, or you'll see the graph that we have here that represents our time as the independent variable. And notice S as the dependent variable. S is in meters. Now, notice here what S is representing. S is the distance away from his house. Okay? Now, in this case, we are able to use distance and displacement synonymously. Okay? And there's actually the first question at the bottom, or the first part at the bottom says, explain why S of t should be an increasing function. Why is it always going to be increasing?
Because he's going constantly in the same direction away from his house.
Yeah, he's constantly getting further from his house. He's constantly going the same direction. Okay? He doesn't turn around at some point. It's not like, okay, he's riding up the hill, up the hill, up the hill, up the hill. He reaches a peak, now he's going downhill, and he's going so fast that the wind catches his hat and blows it off, so now he has to turn around and go back, and then... No, that's not happening here. Okay? He doesn't have to turn around for any reason. So, in this case, because there is no change of direction, the displacement and the distance traveled will be the same. Okay? Now, in our later lessons, we'll look at how to deal with finding total distance as opposed to just our final displacement. But again, that's going to be in later lessons. All right? Now, let's talk about part B down here. A function for Michael's speed. All right, again, because there's no direction, there's no change in direction here, we can use speed and velocity synonymously. Okay? The speed is always going to be, speed is always positive, but velocity is always positive in this case as well. Again, because we never change direction. Okay? So, but could we find a function for speed? What do you guys think?
Yes, because we have distance and time.
Okay, so speed is distance over time, right? Distance over time. And specifically, yeah, what?
Since we're using S for displacement or distance or whatever, how would we represent speed? Like what variable do we use for speed?
You could use V for velocity. In this case, speed and velocity are the same.
Okay.
And then we'll use V of t. If I wanted the speed, I would give absolute value of velocity to get my speed. Okay? So that's what we're dealing with here. Speed is the absolute value of velocity. In this case, we know velocity is always going to be positive because we never change direction. So we can just say it's v of t in this case. Okay?
Okay.
Now, let's keep thinking about this distance over time thing. It's really what we're thinking about is the change in distance, right? Over the change in time. Well, the change in distance is the s, right? So that's ds. And what's change in time? dt. Well, what's ds dt? That's the derivative, or slope. It's the derivative. If we want instantaneous velocity or instantaneous speed, okay,
Wait, what?
our speed, our average speed is just distance over time, right?
Yeah.
Well, if we wanted instantaneous speed,
Any given point.
okay, at any given point, then we're talking about derivatives, okay? So we have ds dt, or we could call that s prime of t. And that is our velocity function, okay? So, since we were given s of t up above here, what is s prime of t?
3.6 t squared minus 60 t plus 284. Oh, I mean 285.
Very good, okay? We take the derivative of that of that s of t up at the top here, okay? Take that derivative, and this is what we've got down here. So there's a function that represents our speed at any given time. That function always is above the x-axis. Okay, notice the y-intercept is above the x-axis, and actually, what shape is this?
Square.
T is squared, it's quadratic, so there's a parabola opening up. Our vertex is actually going to be above the x-axis too. Alright, it's never going to be negative.
Can I go to the bathroom real quick?
Alright, so now let's take this one more step further. What is acceleration? It's change in velocity over time, right? So your acceleration is the change in velocity over time. So guess what? They kind of gave us a little hint there. That's our second derivative of the displacement. Okay? If you want, you can, that's the first derivative of the velocity, which is the second derivative of the displacement. Okay?
So you're finding the slope of, like you're replacing, I guess, the original function with the velocity function and taking the slope of that.
Mm-hmm. Yeah, it's a rate of change of the rate of change. So you're taking the derivative of the derivative. Okay? So then for D, what are we going to do?
Plugging 15 to the velocity and acceleration function.
Yeah. Yeah, plug 15 into the two answers that we just got. So go ahead and take a second and do that, just so we can then describe what Michael is doing at the 15-minute mark. Yeah, so this s double prime, notice, is a linear function. It's going to be 7.2 t minus 60. Okay? We mentioned it was v prime of t, but we didn't actually find it yet. Okay, so just so that we know, if we were to first of all find our displacement at 15 minutes, we can find out that Michael is actually 1,575 meters away from home. Okay. But let's talk about what his speed or velocity is, and also what the acceleration is. Okay? So, velocity. How fast was he going?
195 meters per second.
195 meters per
Minute.
minute. Okay. Meters per minute. Alright. And how about the acceleration?
48 meters per minute squared.
48.
Yeah, 48 meters per minute squared. Okay. So, can you tell me, has he gotten over the hill, or is he still going up the hill at this point?
Go down.
Yeah, he's
What makes you say that?
What acceleration is positive? Oh. Oh.
oh, he's over.
Isn't he done?
Oh, we don't know yet.
We
If
don't.
you look at the graph, if you look at where time is 15,
Uh-huh.
the acceleration's increasing again, so that hints at him going downhill, so he's already over the hill. But that's not really like math.
Okay. Well, the acceleration is positive, which means his what is increasing?
His velocity.
His velocity is increasing. So that does indicate that we're going downhill. He's picking up speed.
Yeah.
All right. The longer he was going uphill, the slower he's going. Okay. Until finally he reaches the top. And then he's able to start picking up speed. Okay. So, yeah, we're on our way downhill at this point. Okay. Now let's look at the this last question is really a good question. At what point do you think the hill was the steepest?
Only slowest point.
What?
Wherever he was the slowest.
Okay. Where he was the slowest.
Can you just look at it and say it?
We just graphed it really quick.
We could find it exactly.
Can
How would we find where it's the slowest?
Find the min of the derivative.
The min of the derivative. Yeah. Okay. So, so at the min of the velocity function, right? So how do you find the minimum of the velocity function?
maybe go to 0, solve it out, and then do the whole plugging in values from
Make what equal to 0?
the derivative, the velocity function.
Well, if the velocity is 0, then the velocity is 0, right?
Oh, it's
Oh, the acceleration.
Aha.
acceleration function.
There we go. Okay. So that's going to be when the acceleration equals 0. All right? Which that's kind of nice because that's a nice easy equation to solve. 7.2 t minus 60 equals 0. So t is
60 over 7.
yeah, 60 over 7.2, which is 8 1/3. And that's minutes, right? Now this asks at what point. All right, so that is the time. It also asks us for how far had he traveled. So we need to get S of 8 1/3. What's S of 8 1/3? Yeah, okay, so that's 35 meters per minute. So that's the slowest he goes. That's when it's the steepest. Now, we're making an assumption here about that word steepest.
You can do that fast.
Say that again, Adam.
You can be the fastest.
Yes. It could be steepest against us, which is right here, or it could be the steepest for us, which means that our acceleration or our velocity would be a maximum. Okay? Now, there's only one critical value here. So how would we find where he was the fastest? Think back to our optimization problems.
Oh my god.
No.
Oh, come on.
The maximum of the velocity.
The maximum of the velocity, but the velocity is a parabola, right?
Yeah.
So we know that wait a sec. This was not S. This was velocity. Sorry. He's going 35 meters per minute. That's the slowest he's going the whole time, which means anything on either side of that is going to be higher. So where would the maximum be?
At final distance.
At where?
The top of the
The
hill.
top, like at the bottom of the hill, like at his destination.
Okay, either at his destination or at his starting point, right? Either at the beginning or at the end. Remember, in optimization problems, the optimal points always occurred either at a critical point or at the end points of the interval that you're given. So we would want to look at v of 0 and v of 19. Okay? If you plug in v of 0, you'll notice we get 285 meters per minute. Now, because we're going uphill, we know that it's automatically going to be slowing us down, okay? The other thing would be, would be at v of 19, which if you plug that in, you get 444 point something, okay? That's meters per minute. Notice we're going much, much faster, okay? And another way you can think about this is where the acceleration is a maximum. Okay? Well, the acceleration we know is linear with a positive slope. Okay? So that means acceleration is going to be increasing the entire time. Okay? It's negative for a while, but it's negative, but it's increasing the entire time. Okay? So when is the acceleration at a max? Well, at 19, yeah. Okay? So the acceleration at time equals 19 would be, let's see, 144, 142.8 minus 60, so 82.8. Is that right? 7.2 times 19 minus 60.
76.8.
76.8?
Yeah.
Okay. Lost something in there. Okay. So that's his greatest acceleration. So there we can see it's steepest. Okay. It's steepest at t equals 19. And then we can go ahead and plug that. It says how far had he traveled at this point? Well, that was his destination, right?
So it should be 1,575.
No, 2,500.
Should be 2,500. Okay. So S of 19 was 2,500 meters. Okay. All right, so that's a kind of a problem that we could address. Now, a lot of that was a little bit, we had to really think about the situation and whatnot. As we look at kinematics a lot more through the upcoming lessons here, it's actually a lot more straightforward than this. Okay? And that is because of the different relationships that we're going to be able to see. Okay? Kinematics, we're talking about a displacement function showing motion along a path. A couple of things here. If we are to the right or above where we started, then our displacement's going to be positive. If we're to the left or below where we started, then our displacement will be negative. Okay? But one thing to note here is that the distance is the absolute value of the displacement. Okay? And we're going to have to really be careful in how we work with that. Okay? We already mentioned the term the motion graph. Now the motion graph, it's going to be similar to what you saw earlier and similar to what we did with parametric equations before. You're going to plot a point on the number line, but you should also then label it with the time. Okay? And then finally, just seeing the relationship here. And this is where we'll pick up tomorrow and do some applications and things here. If S of t, which you may also see, we're using S of t, you may also see it as x of t. It really doesn't matter, you can use whatever letters you want, but you'll often see it in our book as S of t, or you'll see it as x of t. If you take the derivative, you've got velocity. If you take the derivative of velocity, you have acceleration. And notice here, this is a term that you need to make sure that you know, initial conditions. The initial conditions are S of 0, V of 0, and A of 0. Do not assume that we always start at 0, start with a 0 velocity, and start with a 0 acceleration. Okay, that's a really common mistake that people make. Use the actual functions that you're given and find what those initial conditions are. When they say describe the motion of an object at a specific time, you should give all three of these. Okay? You should say it is at this position, moving with this velocity, with this acceleration. Okay? So there should be, you should have all of that information if you're asked to describe something's motion. Okay? Alright, so that's an introduction here to kinematics and kind of get us thinking along those lines as we address this last unit of our course.